confusion about all those P terms like pH, PI, pKa, pKR, and so I thought I'd do a little video to review. I was a little nervous to bring in the Cookie Monster analogy to class, not gonna lie, but since it seemed to help, we're gonna bring it back. But first, here's just a quick summary for those who just want the gist. The pH is a measure of free proton availability. It's a measure of like the solution, and it's gonna be the combined effects of all the acids and bases in the mixture. The pKa, that's the measure of an individual acid site strength. So an individual deprotonation site will have a pKa. And the higher that value is, the weaker the acid, the lower it is, the stronger the acid. It represents the pH at which half of it is protonated and half of it is deprotonated. pKr, that's just a term we give for the pKa of an amino acid's R group or side chain. Some amino acids have them, some don't, but that's what that's for. You also see that basically there's this point called the pi. The pi is the isolectric point. It's the point at which a molecule is electrically neutral, so it's uncharged. And so if you have a multi-protic thing, you have lots of sites that can act as proton donors, you're going to have some point at which that molecule is electrically net neutral, and this is your pi, this is your isoelectric point. We can calculate that for like anything that's multiprotic, so it could be like an amino acid, it could be a buffer molecule that has multiple protonation sites, or it could be an entire protein. Thank goodness for computers. So all of these different terms, they're all connected to that pH though, because that pH is a measure of the free proton availability, and so that's going to influence whether or not that you see something in its protonated or its deprotonated state. So let's dive in. The Cookie Monster's coming to town. Let's go to the party. So if you think of the pH, instead of in terms of just like protons, if you think of it kind of proton jar, we'll think of it as a cookie jar. Well, now basically what happens is if you have a full cookie jar, this is like you have a high proton concentration, you have a low pH, you have an acidic environment. But if you have your jar is pretty empty, this is like having a basic environment, a high pH. Now, how full that protein jar is, that's going to be basically your pH. So, but remember, it's an inverse log. So basically, the fuller your cookie jar, the lower the pH, the more acidic the environment. So you have this cookie jar, say your water, and you have based on the autoionization of water, you have some amount of, a very, very small amount, but still an appreciable amount of ionized form. So of your hydronium ion and of your hydroxyl ion. And so the hydronium ions, what we're going to be caring about here, that's our cookie jar, that's our proton, because remember, those protons aren't just floating around as H+, they're latching onto a water molecule. So your water, you start out with some fullness of your cookie jar. But now what's going to happen? Now you invite over some friends. You invite over some friends for your party. And some of those friends, they're going to come and they're going to come with cookies. And they're going to come and they're going to donate cookies. And those friends are going to be acids. But some of the friends, they might be more generous with their cookie giving than other friends. So some of the acids are going to donate to that jar, even if that jar is already really full, because they're just so generous. They're just going to donate it no matter what. And so that would be like a strong acid. But what if you have something that's kind of more wishy-washy, like, well, I guess I'll donate, but I kind of want the cookie for myself as well. And so therefore, if the cookie jar is already pretty full, it might think like, okay, well, there's plenty for other people, so why should I donate my cookie? I'll hold on to my cookie. And so this would be more like a weak acid. And only when the protein jar was getting really low, only when there weren't enough cookies for like everyone to go around or whatever, they might go ahead and give it up. And so really, it's not this simple. Really, what's happening is that if you have stronger acid, it's going to be less likely to hold on to that proton. It's less likely to hold on to that cookie. But what's going to happen is that a higher proton availability, when your jar is fuller, when your pH is lower, there's going to be lots of cookies around so that if it drops its cookie, you can find another cookie. But if that jar is pretty empty, then if it drops its cookie, it can't really find another cookie very easily.
And therefore, the proton availability, the pH, is going to directly influence whether or not you're going to find the acid with a cookie or without a cookie, whether you'll find it in its conjugate acid form with the cookie or in its conjugate base form without the cookie. Speaking of bases, what if you add a base? What if some of your friends, they come without a cookie? And some of them come really, really hungry. And that would be like a strong base. They're going to take a cookie even if that jar is really low. They really want that cookie. But then there's going to be friends that maybe they're like, I'm hungry, but I mean, there's not that many cookies. I don't want to take them if other people need them. And so that would be more like a weak base. And again, it's not really like this. It's not like that. It's just that they're not going to hold on to them that tightly. And if they're not holding on to them that tightly, then and there's less of them around, well, they're more likely to just like not have a cookie if you were to go and find them at the party. But if there's more around, then you might be more likely to find them with the cookie. And so this would be how we can talk about the strength of an acid or a base. So at the end of the night, how many cookies there are in the jar was going to depend on how many of each type of friend there were and how greedy or generous they were. And so how do we describe greediness or generosity? Well, typically we actually describe it in terms of the generosity because we're talking about the acid. When we have a value called the pKa. So that pKa, remember, that's going to be the dissociation constant of the acid. So it's telling you about how much of the acid is going to deprotonate when you get like to equilibrium. And so at this point where you have the pKa, this is going to also be the pH at which half of it is deprotonated and is this in its conjugate base form. So half of that acid has given up its cookie and it's in the conjugate base form at that pH. Because remember, the pH is going to be a measure of the proton availability. It's going to be a measure of how full that cookie jar is. And how full that cookie jar is matters because different friends will give and take at different levels of the depending on how much protons are available. So some of them, remember, they're not going to give it up until there's not very many in the jar. And so that would be like your weaker acid, where some of them, they're going to donate that cookie even when the jar is really full. And that would be your stronger acid. If we're talking about that jar being really full, what we're saying is that there's a lower pH. And if we're talking about the jar being really empty, we're saying there's a higher pH. And remember that the pKa is going to be the point at which half of it is protonated or half of it is deprotonated. If you have a pKa that's lower, what this means is that half of it is going to be deprotonated at a lower pH at a higher a fuller cookie jar. So basically, this is your stronger acid. So a stronger acid is going to have a lower pKa. Conversely, if you have a higher pKa, what this is saying is that you have to get to that cookie jar to be pretty empty, to be more empty, to be more basic, more alkaline, higher pH, in order for half of it to be deprotonated. And therefore, we can compare the strength of different acids by comparing their pKa's. And the lower pKa, stronger acid, and a higher pKa, a weaker acid. And so when we're dealing with weak acids and bases, we can still talk about them being like stronger or weaker, but we're still within this weak acid base category where we're not thinking about it being fully dissociated, but instead you're going to get some amount of the conjugate acid and the conjugate base. And what proportion you're going to get is going to depend on your pKa, as well as the pH. So it's going to depend on what's around it. Now, how strong an acid is going to kind of depend on the relative strengths of its conjugate acid and its conjugate base form. So the stronger the acid, the weaker its conjugate base. And the stronger the base, the weaker the conjugate acid. What this means is that if you have a way to like stabilize the conjugate base, if you have something like resonance or induction or something like this to stabilize the conjugate base, then you're going to make it so that that base is less likely to act as a base. And so what's going to happen is that you're going to be more likely to find it in that base form. So it can get kind of confusing because the stronger the acid is, the more likely you are to find it in the conjugate base form. And the stronger the base is, the more likely you are to find it in the conjugate acid form. So when you're trying to predict whether an acid will be stronger or weaker, you need to be thinking about, well, which of these forms is going to be more stable? And the more stable form is the happier form, the more thermodynamically favorable form, that's the form that you're going to find it in. So it's important to remember that something can only act as an acid in its protonated state. But the stronger the acid is, the less likely it is to be in that state. And thus, the more likely it is to be in the deprotonated state. And in the deprotonated state, so that conjugate base form, well, now it can only act as a base. Once your friend gives up that cookie, it can only take a cookie. It doesn't have another cookie to give up. So if the molecule is neutral in its protonated state, though, if that's neutral in its conjugate acid, well, now when it deprotonates, it gives up that proton, that positively charged proton. Well, now it's going to be negatively charged in its conjugate base form. But some molecules are positively charged in their protonated state. So the conjugate acid is going to be positively charged, and therefore they'll be neutral in their deprotonated state, so in their conjugate base state. So we can't simply look at charge to tell us whether something is like an acid or a base or something like this. And so some acids are neutral in their protonated state and some are positively charged in their protonated state, but they're always going to be one charge less in their deprotonated state, but that could be neutral and that could be negatively charged. And this is all assuming that we're talking about a single site. So when we're talking about a single site, we can talk about in terms of a pKa, the pKa for that site. And remember that at when the pH equals the pKa, you have equal amounts of acid and base. If you're below that pKa, well, now that jar is fuller, there's more protons around, you're more likely to be protonated. But if you're above the pKa, well, now there's fewer protons around, that jar is more empty, and so you're more likely to be deprotonated. And this is true no matter what acid we're talking about. But what's going to change is the pKa. Different acids, different protonizable sites are going to have, or deprotonizable sites are going to have different pKas. So the pKa is going to kind of set the cutoff point. Where is that 50-50 mark? Where is it that half of them will be protonated and half of it will be deprotonated? And so remember that if you have a stronger acid, basically what that means is you're going to have a lower pKa. That jar is going to be more full when you draw that 50-50 line because you're more generous. And if you have a higher pKa, well, now our line is going to be, we're going to be shifted to the right, and we're going to basically say that that jar has to be more empty before we can donate. So different acids will have different pKa's, and therefore they'll be at different places within that spectrum. And we looked at how we can use the Henderson-Hasselbalch equation to figure out the actual proportions of things that are protonated or deprotonated at a different pH based on their pKa. So the Henderson-Hasselbalch equation is awesome. It's going to allow us to do things like calculate what percentage of an amino acid side chain are protonated or deprotonated, as well as do things like prepare buffers. It's also really important, though, to realize that we don't even need to use the Henderson-Hasselbalch equation. So basically, what happens is that for each pH unit away from the pKa that you go, you're going to get tenfold more of one form. And so if you go one pH unit above your pKa, well, now we're saying there are fewer protons around. That cookie jar is more empty. So you're less likely to find things being protonated. You're more likely to have things in the deprotonated state. And you're 10 times more likely in the 1 pH unit above. If you go 2 pH units above, well, now you're going to have 100-fold more of it in the deprotonated state. 3 pH units above, 1,000, 4, 10,000. So you can see that when you're a couple by the time you're a couple pH units away from the pKa, it's predominantly going to be in one form. And if we go the other direction, if we go below the pKa, well, now there's more protons available. So now we have like the opposite situation. We're going to get 10-fold more of the protonated form, and then 100-fold more, and then 1,000-fold more, and then 10,000-fold more. And so basically, if we're a couple units away from the pKa, we don't even need to use the Henderson-Hasselbalch equation to know that almost all of it is going to be in one state. But we can use the Henderson-Hasselbalch equation, and we will use the Henderson-Hasselbalch equation a lot because it's really helpful. Another valuable thing about the pKa is basically it has 50, because it's like that 50-50 point at which there's equal amounts of your acid in your conjugate base. This makes a really great buffer. So a buffer, basically, the point of a buffer is to maintain the pH at a certain value. And what happens is that in order to do that, it needs to be able to counteract anything that comes at it, whether it be an acid or whether it be a base. Because remember, the pH is going to be a measure of proton availability that's coming from the combined effects of all the acids in a solution. And so basically, if you were to add more, then if you were to add a base as well, all of that would draw or take cookies from the jar. So basically, you'd be affecting the pH. And how much you're affecting the pH is going to depend on like, well, how much acid and base are around to kind of counteract that effect. And so if you wanted to counteract the effect of an added base, you would need an acid. And if you wanted to counteract the effects of an added acid, you would need a base. And so in order to be best prepared to counteract either, you'd want equal amounts of your acid or your base. And this occurs at the pKa. And so this is why when we choose a buffer, we want to use a buffer that's going to have a pKa that is that is as close as possible, basically, to the pH that we wish to stabilize, because that's when we have the best buffering capacity. There's about plus or minus 1 pH unit where you still have you have tenfold more of one of them out of 1 pH unit above. You have tenfold more of your conjugate base. And at 1 pH unit below, you have tenfold more of your conjugate acid, but you still have quite a bit of both of them. And so we kind of consider this buffering range to be plus or minus 1 pH unit of the pKa. And that's one of the reasons why we choose different buffers if we want different pHs. So that was a simple case where we just have a single pKa to talk about. But as I mentioned, we often have complicated things in biochemistry. We have things where instead of a single pKa on a molecule, we have multiple. And we might have lots and lots and lots. So a multiprotic acid is like, instead of just inviting a bunch of different friends, you invited a bunch of friends, like separate friends. They all come together and they're linked together. And when these friends are linked together, basically, well, some of them are going to come with cookies and some of them are going to come hungry. And therefore, the pH of your solution is going to depend on the effects of all of these groups like before, but they're going to be on the same molecule. And so now we can talk about a pKa value for each of those different groups, as well as a pi value. So a pi is the isolectric point. It's the pH at which the molecule is neutral overall. So it's saying, okay, well, we have these multiprotic things. So there's multiple groups that can protonate or deprotonate. And what's going to happen is that depending on the pH, you'll find those friends with a cookie or without a cookie. And there's going to be some pH, which we call the isolectric point, at which the molecule is neutral overall. So if you're at a pH that's below your pi, what this means is that there's more protons available, that cookie jar is more full. You're more likely to find those friends with the cookie when you go and find them at your party. So the molecule is more likely to be in the positive state. More copies of it are in the positive state than in the negative state, so you have a net positive charge. But if you're above that pKa, well, now that jar is more empty, you're less likely to find your friends with a cookie. They're more likely to be in that negatively charged state. An example of such a multiprotic molecule are amino acids. So every amino acid has at least 2 pKa groups. It's got the pKa for the carboxylic acid group, and it's got the pKa for the amino group. And remember that the pKa is always going to be telling you about the acid form, about the protonated form. So if we talk about the carboxylic acid form, so if we talk about this COOH, sometimes we refer to this as the pK1, and that's going to be the pKa for this COOH group. and typically that's about 2. It's going to vary a little between the different amino acids for reasons that basically for different reasons, including inductive effects and things like this that are making the thing more or less acidic. But when we're talking about our pK1, this is going to be the pK1. And you'll see that all amino acids are going to have this pK1 because, well, at least in their free floating form, these are going to have that carboxylic acid group. Now, all the amino acids are also going to have a pK2. And the pK2, this is going to correspond to this. So that's going to be our pK2. And that's going to be typically about 9 to 10. And that's going to be the pKa for the NH3 plus group, because remember that the pKa is always going to tell us about the acid form. So the pK2 is going to tell us about the strength of this protonated amine group on our amino acid. And note that it has a higher pKa though, so it's a weaker acid than our carboxylic acid. And well, what did we say before? We said if something was a stronger acid, we're more likely to find it in its conjugate base form because it wants to act as an acid. And so the once it acts as an acid, it's in its conjugate base form. So for our carboxylic acid group, we're going to typically find it in its deprotonated state, in its conjugate base state. But for our amino group, well, here we're saying, okay, well, we have a weaker acid, which means we're more likely to find it as an acid, which means that we're more likely to find it in this protonated state. But of course, this is going to depend on the pH, right? We can compare the two of them and say, yeah, we're more likely to find the COOH deprotonated than we are the NH3 group. But that's all going to depend on the pH. So if you're at a low enough pH, that's going to happen is that both of those groups are going to be protonated. Both of them are going to be in their conjugate acid form. But then as you go up, basically first you're going to go past that first pKa, that pKa for your carboxylic acid group. That's going to deprotonate because that's going to deprotonate first, because remember that things are going to deprotonate in the order of increasing pKa. So you're going to have that carboxylic acid group is going to deprotonate. And then what's going to happen is that the amino group, this is still going to be protonated. But then what's going to happen if you increase the pH even more? Well, now you get that deprotonation of your amino group. And so now you get the conjugate base form. But you have to get to a pH of about 9 to 10 in order for half of that to be deprotonated. So instead, what you're going to find typically is you're going to find that at a pH in our body, you're going to have it in this Witter ionic form where you have a positive charge on the amine group and a negative charge on your carboxyl group. But there's a specific point at which it's exactly like ionically neutral. Because remember, there's going to be like some of it in one form or some of it in another form, depending on how far you are away from the pH. And there's some pH when it's exactly even, when it's exactly neutral. And this is going to be your isoelectric point or your PI. If you only have 2 pKa groups, then the PI is simply the average of the 2. Things get more complicated if you have multiple groups, but if you just have 2, it's just going to be the average of them. So if we take the average of about 2 and about 10, so 2 plus 10 is 12 divided by 2, that gives us about 6 for our isoelectric point, the point at which something is electrically neutral. So isoelectric point, something is electrically neutral. And this is something that's like a multiprotic thing, but it can be like it can be an amino acid, it can be just like a multiprotic, a different multiprotic acid, or we'll see later, we can talk about it in the case of even more complex molecules like proteins, where we have lots and lots of different sites. And with all of those cases, we can use this term PI to refer to the isoelectric point, the point at which it's net neutral. And if in the simplest case, if you just have 2 groups, it's going to be the average of their pKa's. But if you have more, then you have to kind of think through things a little to think about where you would have that 0 point. Because that 0 point is going to come when like in between the pKa's for 2 of them. Okay, so in a little more explicit, we can like draw titration curves. So we can draw a titration curve for glycine, which is basically it only has, it doesn't technically, you can, depending on who you ask, it has a hydrogen as a side chain, or it doesn't even have a side chain at all. Either way, it's not ionizable. You're not going to pull off that proton from the carbon. And so we can just think about there being those two pKa values, the one for the amino terminus, and then the one for our carboxylic acid terminus. And we can think about, okay, well, if we go from a low pH, what's going to happen is we're going to have the amino group protonated, and the carboxylic acid group is going to be protonated. Note that here the 0 is standing for no charge. It's not representing charge here. This is not an O representing an O minus group. This is 0 charge at a low pH. Now, if you were to add the equivalent of one OH minus unit, so you were to deprotonate one group. Well, first you're going to deprotonate the most acidic group. You're going to deprotonate the carboxylic acid group. And that's going to give you a negative charge there, but you're still going to have the positive charge on your amino terminus. But now if you would add another OH group, well, now what's going to happen is you're going to deprotonate that amino terminus as well, the N terminus. And so now what's going to happen is you'll have 0 charge there instead of that positive charge. And so now you have a charge of -1. So you can see that in this middle state, the 0, the pH at which we see this is going to be our PI, our isoelectric point. And what we could do is we could actually go ahead and we can draw titration curves for amino acids or for any thing that's multiprotic. And what we'll see is basically, as you'll have buffering regions around the two different groups. So remember the buffering regions typically like 1 pH unit plus or above the pKa. But in this case, we have 2 pKa values because we have one for the carboxylic acid group that's about 2.34, and then one for the protonated amine group, our N terminus, that's about 9.6 in the case of glycine. And so what's going to happen is you get these two flattish regions, these buffering regions around those points. And then in between them, you get your isoelectric point, the point at which they're electrically neutral. What's going to happen as you add OH minus is basically you're going to start deprotonating that carboxylic acid group. At your pK1, you have equal amounts of the acid and the base at that one site, that carboxylic acid site. So you have plenty of the acid form to counteract the added base, but you still don't have deprotonation of your amino group. So that's not going to be able to help you counteract that. It's not until you add more OH minus that then you get in the range where you're starting to deprotonate some of that. Amino group, and then this is going to provide buffering capacity for a while, but then your pH is going to shoot back up. Your PI, the isoelectric point, well, that's that point at which the molecule is neutral overall. And so that represents this point where we're in this Zwitter-ionic form of the molecule. This is going to be our PI. It's going to be the average of the two of these. But if you were to look at a chart of amino acids and their different pKa values, what you'll see is that things are actually more complicated. So instead of all of them being nice like glycine and just having a 2 pKa values, sometimes what we get is we get an ionizable side group. And so what we get is we get a pKr. So the pKr equals the pKa for an R group of an amino acid. That's going to be our pKr. And you'll see that only some of them are going to have pKr values. And this is because only some of them have ionizable side chains. So there are the main ones that we talk about when we talk about like ionizable ones are going to be histidine, lysine, arginine, aspartic acid or aspartate, and glutamic acid / glutamate. These are going to be the main ones we talk about, but then tyrosine and cysteine can also ionize, and so you'll find pKa values for them as well, pKr values for them as well. And I'm going to want you to do the same sorts of things for those. But the naming can get kind of confusing because, well, anytime we have a weak acid, we're going to have to talk about its conjugate base as well. And we talk about things going back and forth between the acid and the base. So how do we choose whether we call something basic or we call something acidic? In the case of amino acids, it's based on their neutral form. So let's think first about what's the predominant form at a pH of 7.4. How are we going to go about this? Well, we can go about this by comparing their pKa to the pH. Remember that at a higher pH, there's going to be less protons available. And at a lower pH, there's going to be more protons available. And so what's going to happen is that if you are at a pH that is above your pKa, this means that you're more likely to be in the deprotonated state. But if you're at a pH that is below your pKa, well, now you're more likely to be in the protonated state. And so the pKa, remember, that's going to tell us where we draw that 50-50 line. If that pKa is lower, then we're more likely to be above it. And if that pKa is higher, we're more likely to be below it. And so more specifically, in the case of aspartic acid, say, well, here it's got a pKa of about 4, and we're talking a pKa of about 7.4. So we're talking like 3 pH units away or so. We've got about 1,000-fold more in its deprotonated state. And so for aspartate, we're more likely to find it in its deprotonated state. Glutamate, same deal. What about the basic ones? So histidine is a little bit confusing because histidine is kind of wishy-washy. It's got a pKa that's closer to our pH we're talking about. So you still have significant amounts of histidine in both forms, but which form are you going to have more of it in? Remember that we're still above the pKa. This means that we're going to have more of it in its deprotonated form. What about lysine and arginine, though? These guys have higher pKas. Now we're talking pKas that are above the pH that we're at. And since the pKas are above that, basically what that means is you've got to get that cookie jar really, really full before they donate. And so you're going to be in this state, the cookie jar is full enough for them. And so they're saying like, no, I'm not donating, there's plenty in there. And so for these guys, you're going to find it in its protonated state. So these are going to be the predominant forms that we're going to see. Although with histidine, you'll also see some of each. So you'll have like 5 to 10% of one of them or whatever. But your the predominant form, the main form would actually be that deprotonated form. Okay, so now in that main form, is it acting as an acid or as a base? So remember back to what we talked about how you need to be protonated in order to be an acid. You need to have a cookie in order to give a cookie. If you're not protonated, you can't act as an acid. So let's look at each of these in turn. If we talk about aspartate and we talk about glutamate, we said that they were more likely to be in their deprotonated state, as well as histidine. In that form, is it going to act as an acid or is it going to act as a base? Well, it can only act as a base, so those are going to act as bases. And well, what about lysine and arginine? We said that they're more likely to be in their protonated form. They're more likely to have cookies. So they can't take another cookie, their hands are full. Instead, they can only donate a cookie. They can only act as an acid. So in those dominant forms, those ones we call basic, a lot of them are actually acting as acids. Lysine and arginine, those are going to be acting as acids. And those ones that we call acidic, aspartate and glutamate, well, they're going to be acting in the conjugate base form. They're going to be acting as bases. But the thing is that they're not they don't want to act as a base very much. And those basic amino acids, basically their conjugate acids don't really want to act as acids. And so what they're done, then they're not gonna. And so they were so happy acting as an acid, or they were so happy acting as a base, that we're going to find them in their conjugate form. We're going to find them as they've already done that. Those cookie monsters have already taken a cookie in the case of the basic amino acids, or they've given up a cookie in the case of the acidic ones. And so then why do we call these basic, or why do we call them acidic? Well, that's because we need to think about their neutral form. The naming is based on whether their neutral form acted as an acid or as a base. So even in the case of histidine, even though unlike those other guys, it actually has a pKa that's below the pH we're normally talking about, well, even then, in its neutral form, it's going to act as a base and pick up that proton. And for the basic amino acids in their neutral form, well, that's the new deprotonated state. And so they're also going to act as a base in the deprotonated state, which is their neutral state. But in the case of our acidic amino acids, well, they're in their neutral state, they're going to be protonated. So unlike those otherwise, when these are protonated, they're neutral. And thus, when they're protonated, that's when they're going to act as an acid. And so we call these the acidic amino acids. And we can draw more complicated titration schemes for these as well. And if you really want to know more, I have videos and I have tutorials and things like this on how you can draw these titration curves. But basically, you just have to realize, okay, well, let's put these in order of the pKa's. And remember that for the ones with an ionizable R group, you're going to have 3 pKa values. The pKa1, so for the carboxylic acid group, the pK2 for your protonated amine group, and then you're going to have the pKR, which would be the pKa for that R group. Put those in order of which is going to get deprotonated first. And then you just have to think about, okay, well, in its protonated state, is it positive or neutral? In its deprotonated state, is it neutral or negative? And then when you do that, you can basically just think about what would happen as you add equivalents of OH minus. So if you add like the amount that's needed to deprotonate one site, and then go and see, okay, well, I'm going to deprotonate the most acidic one, and then we deprotonate the next acidic one, and then we deprotonate the next acidic one. And you can kind of then think about what the charge states would be at each of these different places. And then you can draw titration curves for these as well. But here things are more complicated because you're actually going to have, like, now you have 3 pKa values to think about. You're going to have 3 buffering zones, and your PI is not going to be the simple average of all of them. Instead, the PI is going to be the average of the 2 pKa's on either side of that 0 point. And so for the case of lysine, the PI is going to be the average of your pKr and the pK2, so the one for your N-terminus. And in the case of glutamate, it's going to be the average of your pK1, the carboxylic acid group, and your pKr. And so it'll be about 3.22. And so that would be an example of like how you would interpret one of these curves. Basically, the PI is going to be the point at which things are electrically neutral. The pKa, well, you have different pKa's for each protonated ionizable site on a molecule. And then the PI is going to be the point at which the molecule is electrically neutral, which you can think about by kind of like sketching things out and seeing, okay, well, the PI is going to be the point at which it is overall neutral. And this point, this is going to happen when you are at the pH that is between the pKa's of the ones on either side of it. So it's kind of confusing, and we don't really like to do that sort of math, especially if we have a protein where instead of dealing with just like a single amino acid, which was complicated enough, right? Well, now we're saying we've got lots of amino acids. So now going back to our proton cookie jar analogy, now instead of just having like one of those like simple, I say simple, something with just a few pKa values, well, now you've got a whole protein. You've got a whole bunch of friends. You've got like a whole busload of friends that are all connected. And some of these are going to burn cookies and some of them are going to want cookies. And so now we have to calculate the PI for that. Thank goodness for computers, right? And so we can use a computer program like XPazi-Prop-Param in order to calculate the PI for a protein. And so remember that the PI, this is the point at which you're electrically neutral. What this means is that if you were to be at a pH that was above that PI, there's going to be fewer protons around. And if there's fewer free protons, well, now your protein is going to be net negative. And so at a higher pH than the PI, you're going to be net negative. And at a lower pH than the PI, well, now there's lots of protons around, and so you're more likely to be positive. And the isoelectric point, the PI, this is the point at which it's neutral. And different proteins are going to have different PIs because they're going to have different makeups of amino acids. So we can think about the PI and the pKa similarly, in that if we're above that value, if we're at a pH above that value, we're more likely to have things be deprotonated. And if we're at a pH below that value, we're more likely to have things be protonated. But there's a distinction because the pKa, this is telling you about like at a single site, is it more or less likely to be protonated or deprotonated? And whether it's protonated, when it's if it's protonated, it might be positive or it might be neutral. And if it's deprotonated, it might be neutral or it might be negative. When we're talking about the pi, we're talking about the isoelectric point, the point at which it is neutral. And so if it is neutral, and then you go up to a higher pH, this means that there's fewer protons around. So you're going to get a negative charge. And you're going to then get a positive charge if you go to a lower pH. And so this is going to be the same in the case of like a single site, in the case of a pKa, but you might be going from 0 to positive, or you might be going from negative to positive as you go, you decrease the pH, and you might be going from positive to neutral or neutral to negative as you increase the pH. And so you're always going to be like changing a charge in that direction. But in the case of the pi, that's where you're at neutral, rather than that's where you're at in like the protonated state. So that's just an important thing to remember, is that the pi, this is talking about overall charge. When we talk about a pKa, that's not telling us about charge, that's telling us about protonation state. So the pi is really useful though, because we can do things in the lab, like take advantage of this relationship between the pH and the pi in order to separate proteins based on their charge. And so we'll talk more about cation exchange chromatography, and basically how, because different proteins have different PIs, they have different charges of the same pH. We can use this to separate proteins based on their charge using these little resin, these little beads that are charged. So some key takeaways. Something can only act as an acid in its protonated state. And so remember that we use HA to represent like a generic weak acid. So that's your friend that comes with a cookie. Only the friends that come with cookies are able to actually donate cookies. And so you're only going to talk about acting as an acid when something's in its protonated state. However, this could be positively charged, or it could be neutral. But regardless, you have that friend that comes with a cookie. Well, now some of your friends are going to be really generous, and they're going to donate a cookie even when the jar is pretty full, and those are going to be your stronger acids. There are going to be other friends that they're not as likely to donate a cookie, and so they kind of want that cookie for themselves. They're going to be a weaker acid. It's not until that jar gets pretty empty that they're going to donate. And so that would be like your weaker acid. That would be something that would have a higher pKa, meaning that that jar has to be more empty in order for them to actually donate. And remember, it's not that simple. It's more just that they don't have as much, that they have a higher affinity for that proton, and so they're more likely to keep latched onto it, and less likely, therefore, to give it up. And then if there's a lower availability around it, well, now if it accidentally drops that cookie, it can't find another cookie. But basically, when we talk about the pKa, we're talking about the strength of the acid. But the stronger the acid is, the more likely it is to actually act as an acid. And if it acts as an acid, well, it gives up that cookie, and now you're less likely to find it with the cookie. And so if you have a stronger acid, you're more likely to find it in its conjugate base form. And if you have a weaker acid, well, now you're more likely to find it in its acid form. And so it can get kind of confusing when we talk about the naming of things like amino acids, because, well, things are in the form that they've acted as, that you find them typically. When we talk about amino acids, we're going to be talking about classifying them as basic or acidic based on their neutral state. So how is something a stronger acid or a stronger base? Well, it has to do with comparing the strength of the conjugate acid and the conjugate base. And that's to do with comparing the similarity, the stability of them. So if you're the form that you're more stable in, that you're more happy in, that's going to be the state that you're going to be finding it in. And so if you can use something like resonance or induction to stabilize one of the states, to stabilize charge, that's going to make that state more favorable. And so then that's why you can have resonance be contributing to both a higher pKa as well as to a lower pKa. So hopefully this helps you with the assignments. Hopefully this helped clarify things, and we can talk about it more in class.